to the next speaker, Robert Szakats from Concoli Observatory in Hungary. So, Robert, please.
Okay, thank you. So, my name is Robert Szakats. I work in Concoli Observatory in Budapest, and I will show you some examples on how smaller telescopes can be used to contribute to solar system science through our measurements and examples here. So, in the era of ELT and big telescopes, there is still a need for some smaller telescopes, I think, because usually they are cheaper to build and to maintain. We can have more of them, and maybe more importantly, I think it's easier to get telescope time on them, and basically they cover a little bit better the globe than the big ones. Of course, there are some downsides to smaller telescopes, like they have lower limiting magnitude, lower resolution, and sometimes they are not in a very good place. And what I mean by that is that they are too low or not in a high mountain or in a bad climate. So that could be a downside, but usually we can use these smaller telescopes too. So what can we do with them? Usually you can do low resolution spectroscopy, you can do photometry of brighter objects, or you can do photometry of very bright objects where a big telescope is not useful or cannot be used because of the saturation probably. You can do astrometry on your measurements, you can do surveys and some long-term monitoring, because sometimes you can get more telescope time for your project. I will show what we have in Hungary right now, and I will show you then some examples when and where our data are used in publications. So the biggest observatory right now is Concoli Observatory. We have a mountain station at Piszkéstető, and we have 3 instruments there. The 1 meter Ricci-Chrétien and Coudet telescope. It has 2 imaging CCDs and 1 low resolution or mid resolution spectrograph. We used this telescope a lot for minor planet or asteroid observations, and the Andor EMCCD, we use that especially for stellar occultations, but I will talk about this later. We have a new 80 centimeter telescope there, and 60 centimeter Schmidt telescope, which is now used only for near-Earth object discoveries. There is a smaller 40 centimeter telescope, but it's out of order now. It's waiting repairs. And in Budapest, we have a 60 centimeter telescope, but nowadays it's mostly used for public outreach. So these are the images of these telescopes. I don't know if you can see my mouse. This is the 1 meter telescope, the Schmidt, the 80 centimeter telescope, and the 60 centimeter telescope. We have a bigger observatory at Szombathely. They have now a similar or basically the same 80 centimeter telescope there, a new one, and an older 60 centimeter telescope. And the University of Szeged has 3 telescopes, a 40 centimeter one at Szeged, and a 50 and 80 centimeter one at Baja Astronomical Observatory. This later one is also the same as the one at Piszkéstető and at Szombathely. So these are the pictures of these telescopes. This is the Szombathely one. This one is the 50 centimeter at Baja, the 80 centimeter at Baja, and the 60 at Szombathely. So what can we do? One thing is the photometry of asteroids. Right now we have a long-term cooperation with Anna Marciniak at Poland in Poznan. We started collaborating in 2016 in the Small Bodies Near and Far project. So far, we made a lot of measurements for her for modeling asteroids. As you can see, at Piszkéstető, we have more than 100 nights of observations, almost 100 with the Schmidt telescope, 150 with the 1 meter telescope, and 15 nights with the 80 centimeter telescope. So photometry basically looks like this, that you took a photo of the sky and the asteroid is slowly moving in the field of view, and you are measuring its brightness using comparison stars in the field. So it's a very basic technique, but it can be very useful. So I would like to show a few cases where our measurements were used. I won't talk about this too much because in the previous presentation we heard how this shape modeling works. So one of the minor planets in Joseph's paper were observed with our telescopes too. Of course, it was observed with the VLT sphere instrument. There were some stellar occultations that were used in the shape modeling, and of course some optical right curves from archives and from other new measurements, including our one from Piszkéstető. And as we saw, they use the Adam model to get the shape model and the precise axis and parameters of the asteroid. You can see here I think the first and the third row is the model data, and the second and fourth row is the VLT measurements. So you can see how the axis is pointing in the different phases of the asteroid here. Another example is from Edita's paper. Here also photometric disintegrated observations were used from our measurements, and of course from other sources, from, for example, Geiger-GOSA, and there were some space measurements from the Kepler K2 program, where there was some dedicated asteroid measurements, and from the TRAPPIST telescopes. And they use the SAGE model with the thermophysical modeling and occultations to get the right scale of these models, or the right size of or the exact size of the asteroid. So here are some examples. The left side is the SAGE model, the right side is the Adam model, and we can see here two examples, the Irene asteroid and Leto here. And as I said, in this work also measurements with smaller telescopes were used. Other example from Anna's paper, where she determined properties of 16 slowly rotating asteroids. The challenge here is that from ground-based observations, it's a little bit harder to cover all the phase if the asteroid's rotation is very long, or the period is very long and it rotates slowly. So Anna organized an observational campaign, and from long-term ground-based photometric campaigns, she collected the light curves, and it was complemented with also space-based data from Kepler K2 TESS and the SuperVASP program. And to do the convex inversion thermophysical model, or to apply that, they needed some thermal data from space-based thermal observatories like IRA, Szakats, and WISE. And with the help of all these measurements, they could determine the scale, the spin and shape of the models, and the thermal inertia, albedo, and the surface roughness of these asteroids. Here's an example of a composite light curve. This is, I don't know if I can pronounce it right, but crisis, I don't know. But you can see that in different aspect angles, the light curve looks quite different, as we saw it in the previous presentation too. And here also our measurements were used to create these light curves, but again, many other observations were also used where smaller ground-based telescopes were used. So another type of measurement is the occultation measurements. Basically here you can see a small eclipse of a star when an asteroid moves before the star and between the Earth and the observer. So on the right side, hopefully you can see a star here brightening and dimming. The dimming is when the asteroid comes between the observer and the star, and when it goes along the line of sight, it will go away and the star will bright up again. There are some projections for these events. For example, the Lucky Star project is doing projections, and when there is a new projected occultation, you can join this observations and try to catch an occultation. So from occultation data, you can determine the apparent size and the shape of the asteroid via these chords. So when you have multiple observers of the same event, you can basically get some kind of apparent shape and size. So one application of this was used in 2020 by Flavia Rommel. They used these occultations to do precise astrometry on these asteroids to determine their exact position, and combined it with the Gaia DR2 data. They achieved very precise astrometric positions for these TNOs and the 4 Centaurs. And with this, they could, or anybody who want to calculate the ephemerides can do more precise ephemerides, and this can lead to more precise predictions for these occultation events in the future. So here are some examples of the light curves of the occultation. You can see that on the left side, that here and here there is the event when the asteroid occults the star, and in the right side you can see the difference between the old astrometric solution for these asteroids and the difference between the new solution. You can see that there are some big differences, so it's a quite useful tool to do a more precise astrometric solution for these for asteroids on a global scale. Another nice example where occultation data were used by smaller telescopes is the determination of physical parameters of the Haumea. And there was a discovery of its ring that came also from these occultation measurements. Here are the light curves of the occultation, and you can see here that these smaller dims are the ring around Haumea. So in some cases it was detected by the different observers, and here is the light curve of the asteroid made by a 0.8 meter telescope, and this was used to determine when what was the rotational phase when the occultation occurred. So you can make these shape models or shapes from these quartz here, and you can some can fit it with the solution, and also you can do the same for the ring here. So it was a really nice observation, and again, small telescopes were used. I think the biggest one was a 2-meter telescope here, but there were some half-meter telescopes too. So you can do good science and good measurements with smaller telescopes as well. And one other project is right now in our observatory. It's the Near-Earth Asteroid Search Program. Our colleagues installed a new big camera on the Schmidt telescope, and right now you can see the field of view on the left side. So it's 3 degrees by 3 degrees. This is the Pleiades, the M35. So it's a really nice big field of view, and our colleagues are trying to find near-Earth asteroids every clear night with this telescope now. You can see some examples on the right side for detections. The bottom two, they are moving slowly, so maybe you can see here them, this one and this one. They are very faint, but you can see them. And there are 2 faster ones here and at the upper panels. You can see that they are leaving a trail because they are moving very fast, but the algorithms and the optical observation by the observer's eye can find these faster moving asteroids too in these frames. So to sum it up, I hope I could show you some cases where smaller telescopes were still useful for observations, and I think the main giveaway here is that you can do good science and you can contribute to astronomy using smaller telescopes too, that observational data in this field is very important and very useful. So if you have a telescope or if you want to contribute to astronomy and science, you can join bigger observational campaigns like Gaia-GOSA or Lucky Star, and you can do your own measurements too, or observations. And thank you very much.
Thank you for this very interesting talk and for presenting the possibilities of joining with smaller telescopes. I was really impressed by the number of telescopes that you got in Hungary. Okay, if there are any questions, so please ask. And if not, I've got a question. Okay, Grażyna?
Yes, you are first.
So I would like to ask about the weather conditions in Hungary. How many clear nights do you have in a year with respect to the cloudy ones?
Yeah, I can tell only for Piszkéstető because I work there. Unfortunately, not very much. I think on average the third of the year is useful or can be used. So that's when the sky is pretty clear and you can do good observations. And the other 2/3 is like halfway. Half bad and very bad. So unfortunately, we only have mountains up to 1 kilometer in height, and Piszkéstető is around 900 meters. So clouds in the upper atmosphere can be an issue to us, and also wind and humidity. So yeah, it's 1/3 of the year is good, but the other 2/3 is not very good. So yeah.
Okay, thank you. Glazina?
I'm glad that there are 2 telescopes from this observatory in the Europlanet telescope network, and everybody is welcome to apply for the observing time on this observatory. And I believe that Robert will help in elaborating the application if necessary. So you are welcome to observe at this observatory.
Yep. Yeah, you can apply for an observation time. We work in 3 trimesters in a year, so 4 months each, and you can apply at the last month of the previous trimester. So the next one will be in April. I don't know if we have these websites in English on our webpage, but if you contact me and if you want to have telescope time, I can help you with that. Yeah.
Okay, that's great news for many observers, I think. Okay, thank you once again for the talk, and if there will be questions, they can be given on the chat. Okay,